Malheureusement, on n'a pas demandé qu'on rédige pour...
We are ready.
You can ask your questions.
Yeah, I'm asking.
Ça tourne pas là, hein? Ton compteur fixe, là, 18.
So I have not to look on the camera.
You look at me.
Only to
We
the
talk
television.
together.
Exactly.
Yeah. Okay. Madame Razeghi, we're very happy to have been able to capture you in your known home surroundings while we have a chance to come here and talk to you. On peut couper? On peut réaller.
On continue, dans la foulée, allez-y, recommencez.
Okay. Madame Razeghi, we are very happy that we've been able to come to meet you in your normal surroundings in a very busy schedule. We will be talking to you, we'll be enjoying your wisdom about what you're doing in view of telling people in Europe what your background is, getting to know yourself a little better, and finally hearing about your achievements in technology and in basic research. We came in touch with you when you were organizing the conference in Aachen last fall, by which we were able to diffuse to the Europace clients all over Europe an interesting reportage on the state of the art in optoelectronics and photonics. In your opening speech, you made it clear that basic research must not be forgotten. And my first question, therefore, to you as a researcher in Thomson is, are you at all able to do basic research in Thomson?
Thank you very much. I have to say that it's a great honor for me to have you here and to have the opportunity to discuss with each other a kind of overview of my experience, my activities at Thomson during 10 years. First of all, why SPIE conference last year? Because it's a big job, a lot of responsibility, and especially with the research, it's much better to do the research instead of to organize the conference. But the reason that I did it and I accepted to do last year, because it was the anniversary of 10 years activities at Thomson. When I arrived at the end of 1980 from Orsay University to Thomson, it was only to learn a little about technology for my student. And after a short interview with the director of Central Research Labs, that at the time it was Dr. Spitz and Dr. Leclerc, so they insisted I stay there because one part they showed me something that is for the first time in the world. So the word of first time in the world, it was important for me. And at the same time, I found that, they told me, here, if you have if you like to do something, you can do. There is nothing neither related to sex, to nationalities, or to religion. It depends on the capability of the researcher. So it was the reason I stayed there. I came here for 1 month, and it's 10 years. Okay, the results that I achieved during the 10 years, I have to say, it's considerable. It means that I did the things that the Japanese mentioned, that it's I do the magic. Or in United States, they say that, okay, it's impossible, everything I do, it's not possible to repeat it. But I have to say, thanks to the politics of Thomson, thanks to the facility that I had, thanks to the excellent people that I was surrounded by them, and it gave the results that for 10 years, everything that we did, it was not only the high-level research, collaborating with the Nobel Prize or the excellent physicists, scientists everywhere in the world, but at the same time to finish to do the result for the development and production. At Thomson today we have indium phosphide GaN diodes. We have gallium indium oxide indium phosphide photodetector. We have 1.3 micron, 1.5 micron lasers. That everything is, Thomson was the first to put in the production before that even the Japanese and the American be able to do in the research lab, of course with the technique that we developed at Thomson. But I have to say it's not the first time that we have the excellent result at Thomson. Or the people like me can do something. It means that it's again when you are in Europe, when you are in United States, in everywhere in the world, they know that Thomson, likes IBM, it's a very high level industry and gives the opportunity to the excellent research and to do everything that any kind of researcher, engineer can really, if likes, to do that. So that's the first part of my, the reason that, okay, I did this conference because it was 10 years.
Okay, you mentioned IBM, and the achievements of IBM researchers lately have been very well noticed. Notably, Nobel Prizes are coming that way. Thomson has yet to have a Nobel Prize, but I here hold a letter which is a Christmas card to you from von Klitzing, who is the former Nobel Prize winner in physics for the quantum Hall effect, which people know very well. He's writing to you, "Dear Manijeh, for the research work for the second Nobel Prize." Yes. Okay.
Allô, allô. Non, s'il vous plaît, vous pouvez rappeler après. D'accord, merci.
We'll start over again. I'm reading a Christmas card that you received from Klaus von Klitzing, who was awarded the Nobel Prize in Physics earlier on for his research in the quantum Hall effect, surface phenomena on MOS devices. He's asking you, he's saying, "Dear Manijeh, for the research work for the second Nobel Prize, of course shared with you, it would be helpful if I could get a good gallium indium phosphide, gallium arsenide sample which shows well-resolved spin levels." Have you any comments on that?
Yes, it's the, if you look on the conference that I organized, we had 500 experts from 35 countries in the world. And all of them, they were my reference when I started to work at Thomson. If you look, von Klitzing, Dan Tsui, and a lot of scientists that I have the opportunity to collaborate with them and to contact with them, because everything that, at least in this area, I did and we did at Thomson, it was something that in usual it was impossible. So I wanted to show that one part, impossible is impossible, impossible is not friend. On the other hand, at Thomson, we can do something that even somebody like von Klitzing, the Nobel Prize for the fundamental physics, respected and say that it's important. And at the time that he asked that, he knows that, okay, it's possible to have here, but for myself, it was something that I couldn't believe that it's impossible. But that's the kind of things everybody knows. For to have something, it's enough to say it's impossible with me, because I know that I have the possibility here with the excellent people that I'm surrounded with, and the possibility that we have to try to do that. Because again, I repeat, nothing, we are not creating anything, we are not inventing anything, we are finding everything that is exists. And now, the problem in future, in optoelectronic, for industry, for production, is to know perfectly, to have a control of material, the science, the physics of materials, and after that to switch toward the device and systems. So I hope and I wish we can continue at Thomson exactly the possibility that we had during the last decade. So yes, I have to say this kind of letters, this kind of the notice show that really we have to be the proud of our industry and the things that we are doing, and to continue, especially for the young scientists and the young student, to have one part, to know one thing. Nobel Prize is only for the researcher that they continue to do something. You are right to mention that at IBM, even when you look at IBM in Zurich, there is 3 Nobel Prize for 150 researchers. But if you look all of these Nobel Prize, they never be really very respected by industry before to have the Nobel Prize, but they believe themselves on the subject that they did. So something that I would like to tell through this interview and this kind of letters that I showed, to say that we have not to look on the outside and to follow like a motto. We have to have our own ideas, and if we are confident on ourselves and if we believe on something, to continue and to be sure that we are going to be successful.
I would then like to ask you, you have an incredible number of papers that you have been part of, that you have been writing yourself, and a book, which we'll come back to. But a lot of people all over the world owe a lot of their fame to having been able to get materials from you. And I'm quoting from a conference in Japan that somebody wrote about the conference on MOCVD. It's here called MOVPE, metal organic vapor phase epitaxy. And we'll come back and talk about the techniques and technologies involved. But I'd like to quote from this. The conference started with an almost traditional invited paper by one of the most prominent workers in MOVPE, Dr. Manijeh of Thomson CSF. In a keynote address, Dr. Razeghi outlined the sheer diversity and potential of MOVPE with a catalogue of firsts of new materials, highest mobilities, sharpest interfaces, and new devices. One delegate described Dr. Razeghi as a Madonna of MOVPE in her grotto south of Paris, producing material miracles, while another referred to this type of work as the essential driving force in the development of MOVPE as an explorative and diversifying technique. So on with the diversity. You must, of course, be happy when this comes your way. But I'm one of the people who recognize and who know a little about your work from a neighboring area, and I know how many people look to you, maybe not as a Madonna, not even as the queen, but certainly as the mother of MOCVD. And I think that you're probably more pleased to have that feeling that a lot of young people actually are your children, in the sense that they have been able to get their materials from you in order to proliferate in their field, in order to get a good start in an interesting area. I think that it's probably to be too flattering to you, and probably knowing you're too modest to want to continue this discussion. So I think we should pass on to your next item on my list of things that I'd like to discuss with you, which is your book. You said in a discussion we had earlier today that by and large you had been getting good feedback, you'd been getting good reviews of your book. But there was a particular instance where you were not quite happy, namely with somebody who said that from another country, a neighboring country, that you were overlooking sort of the work which is going on in that country. I would like that you comment on it here, that you have a chance to reflect a little on that. Is it true? Are you overlooking other people's work? Are you the dominant driving force in this area in the work? And everybody else depending on you, or do you have some good competitors?
That's a very good question because you are right. First of all, why the book? Because since 5-6 years ago, the different publishers, such as Academic Press, Plunium, Springer Verlag, and IOP, they insisted I write a book on MOCVD. And you have to know that's the first book on MOCVD. Why they insisted I write that? Because I considered that the things that I did with MOCVD, it was not only the usual things. Of course, you have to know MOCVD. I didn't invent MOCVD, neither in the world nor at Thomson. The first MOCVD the technique presented by Manijeh in 1969 in United States for his PhD. And after that, a lot of people in the world everywhere, they did MOCVD. And when I arrived here, Thomson, they worked on MOCVD since 3 years. But something that I did, as in the other field, always we need some people to have a lot of patience and a lot of courage to do something. So usually, when I started to come here to do MOCVD, for me, I didn't know what is that. But only the things it was important for me when I'm in industry. When I do something in research lab at industry, it has to be the first in the world, if not to be the best. If not, it's not research. I have to go to do the development and production. For to be the first, you are always the best. And to be best also when you are the second is much better, okay? So everything that I did, a lot of physics, a lot of things on this, especially in this material that I wrote on this book, indium phosphide system, everything I did, not only the first, also the best. But it's since 1980, 1981. Now, this book, when I wrote, of course, you can imagine how I wrote that, because during 10 years, to have 300 publications and everything, not only to repeat the things, to have the subject that it was recognized by everywhere in the world, it was the results that during when we tried to transfer the laboratories from one part to another part, 1 month in August I have the vacation, so instead of to take the vacation, I tried to write this book. Okay, and now a lot of the review on this book, because first of all it's the first, and secondly, the people know they read it, they like to find their name on that, even if. But the subject of this book was everything that it was the best or the first. So I think that something that I did is correct. And now I'm writing the second volume because they are insisting, and they already, I think that they have a lot of order from that, and they are waiting for the second volume. The second volume is again the same thing. I'm doing the thing, I'm writing about the material, about the devices that again at Thomson we are the leader in the world.
Gallium arsenide.
Gallium arsenide, as you know, we are not the first in gallium arsenide at Thomson, but we are the best. The paper that we have, the things that I'm going to put in the second volume, it's again included everything that it's the first or the best in the world in this area at Thomson that we did. And if in 1 year, 2 years, the second volume appears, because now everybody working on that, the Japanese, American, European, everywhere, okay? But of course, in 2-3 years, some of them, they would like to forget about the result that we did and to say that, okay, we are the best, and they didn't mention our result. But they have to look on the reference and to do some bibliography and to say that everything that I put it here, I was right, it was the first and the best at Thomson.
I think after this convincing explanation of your position and Thomson's position, vis-a-vis writing a book on this subject and what the purpose was, I think we will like to hear from you a little more technical subjects discussed, as what is really MOCVD, not for laymen, but for people who have maybe a feeling for what it is. Could you clarify them on the crucial issues of MOCVD, the companion or competing technique of MBE, point to the differences, and eventually give us a little demonstration of the facilities you have in the lab. So could we start to explain a little about what MOCVD is, and could you give 1 or 2 or 3 examples of things which are uniquely done with that technique and cannot be done otherwise, and that you have done and that you have confidence in will make their way into essentially products. So let's start with MOCVD.
You know, when you look on in science in general, the periodic table, all of the secret of science is in the periodic table. Everything comes from that. If you look during the past 3-4 years, the Nobel Prize in Physics or Chemics, or the chemist, comes from everything that they did with material. You put 2-3 elements together, you have the high temperature superconducting, and you have the Nobel Prize field. You have 2 elements from group, for example, clone 3, clone 5, to put together, you have 3-5 semiconductor. You can do lasers, you can do the transistor, you can do everything. So, something that we need, we know today the importance of material. And when we are speaking about the material, it's not only a kind of cooking, a kind of chemical product without to understand the physics on that. We need the intrinsic material. We need to combine all of these different elements that we have in periodic tables together, to put them together and to combine the advantages of all of them for future, something that we need for future. As I mentioned in my introduction today to the conference, we need to have a magic eyes. Look on your eyes is the most important optoelectronic systems. Look on your head, your brain. It's the most sophisticated computer system. Something that we would like to do that, we would to repeat it and to do that artificially. That's with material, any kind of material. So for that, the technique that we develop at Thomson, technique of metal-organic chemical vapor epitaxy or metal-organic chemical vapor deposition, is today for any elements in periodic table, you have a chemical product. So that's the easiest, cheapest, and the most intelligent way for to have the deposition of this material, to combine them together, to do everything you like. As an example, I would like to show you something. When you look at it's something that one can say it's impossible. It's 6-inch diameter substrate. You have here on that the gallium arsenate 3,5 compounds. And on this material, we put it another kind of material that 1.3 micron, 1.5 micron lasers, and to do something that for everybody it was impossible, and we showed that it's impossible. It's possible for future, but thanks to MOCVD technique. Why? Because it's the technique that help us to do everything, to do one part, the intrinsic material, as you mentioned before, that everybody in the world, all of the good scientists in the world, physicists, in any laboratories, ask to have the collaboration with us, because it's not possible to find really this kind of intrinsic material for to do the good physics with, and at the same time, to do the device for the future. So, this technique, you have in the literature, different technique, liquid phase epitaxy, vapor phase epitaxy, MBE, and MOCVD. So, for future, we tried to really to show that it's the unique technique that you can do everything with. And it's going to replace all of the different technique, and even today, when you are speaking about MOMBE, CBE, is the very low pressure MOCVD, because the MBE people, they found that they cannot do at least the material that it's the basic material for optoelectronic, such as indium phosphide based material for lasers, anything 1.3 micron, 1.5 micron lasers, or the modulator, and so on. So everything is really thanks to this technique, and it's only the technique that we can do that. So
it's okay.
Because after that it's going. Oui, allô? Ah, Alexandre, tu peux me rappeler après, s'il te plaît? Je suis en réunion. So we have to
No, we just go on. We try to make a bridge. That's good.
Okay. And if you...
À quel endroit on va reprendre?
Où on était?
On était où?
No, I can make a question. Je peux poser une question pour
Voilà.
recommencer.
Exactement.
Pour couper, on va avoir un peu de mal.
Oui.
Moi, ce que je propose, si vous êtes d'accord, c'est qu'on prenne 5 minutes pour revoir.
Exactement. Je crois que ça, c'est la meilleure façon.
On est sûr de ne pas reprendre n'importe où.
Tout à fait. Oui.
Donc, on va relire.
Exact.
Hein? D'accord? Ça tourne? On compte jusqu'à 30, hein? On laisse pour que la caméra puisse ensuite on synchroniser au montage. Là, on n'est pas exactement dans le même axe. Monsieur Morgan, vous avez... remettez-vous un peu à gauche parce qu'on voit votre épaule autrement.
À gauche?
Voilà.
Comme ça, oui.
Vous me dites quand on peut y aller, Frédéric? Quand vous voulez.
In an MOCVD system, a typical installation, what is a crucial element?
The crucial element, not for MOCVD technique, for any reactor, any epitaxial reactor, MBE or MOCVD and so on, is the problem of security, is the problem of safety. It means that we are using the chemical product. We have to be very careful with the environment. So that's the first thing. And the second part, the most important problem is not with us, it's with chemists, that they have to work to prepare the product, the chemical product for the starting materials, that they are not dangerous, and at the same time, they are very pure. So that's the first thing. The second part of the MOCVD or MBE reactor is all of the systems, valve or the system that measuring the flow, measuring the quantity of materials. Because when we are working with this the technique, we are speaking about the one atomic layer by one atomic layer. So we need to have the system to be able to measure the quantity as low as a few molecules with excellent precision. So one part is the safety and the starting material, and another part is the systems that measuring the flow, temperature, and different parameters that we have with this technique.
How good are your typical yields, and how does that compare to normal industrial practice? Is it a huge waste, or are you really getting a high yield?
That's the good, excellent question, because especially for industry. We are an industry, everything that we do, we have to speak about the cost, about the yield. 8 years ago, no, 7 years ago, I was invited in NEC in Japan. They gave me confidentially one table that they try to compare the price of one semiconductor lasers made by different techniques, such as liquid phase epitaxy, vapor phase epitaxy, MB and MOCVD. MOCVD is the cheapest, and the yield is the best. But unfortunately, when you are speaking about MOCVD, everybody thinks that, okay, MOCVD is a technique, you can put a technician, is a chemical, you can put the material together, is a kind of cooking, and it's finished. But it's not true. It's a lot of science, a lot of physics, a lot of chemical on that. When you understand the systems, because you are sending the different material, chemical material, you have to know the problem of interaction with the different elements. You have to know the flow pattern, and after that, something that is important to have, one needs a lot of knowledge and experience about the systems, about the material that they do, and after that, when it's optimized, it's the yield, it's much better than the other technique. But again, I'll repeat, one thing that is very important, the people, the scientists that they work with this technique, they have to pay a lot of attention and to like it and to know what they are doing. It's not the things that you can give to a technician to push a button and let's go, because you have a lot of parameters, external parameters, that you cannot control everything only by computer and to push on a button.
MBE has the same problems, I guess.
MBE has a much more important problem than MOCVD. Because the problem of MBE, when you look on an MBE machine, you can see it's much more sophisticated. And it's at very high vacuum. When you have the high vacuum systems, the problem becomes much more complicated. So, when you have the problem with MBE machine, you have to wait 2-3 days or not 2 weeks for somebody to come to do the problem, to repair, and after that, to have the high purity material, you need to prepare the machine more than 1-2 months. But with MOCVD is the question of 1 or 2 hours. Any problem with MOCVD, the problem is a very little money. With MBE, the problem is very high money. Only it's enough to look on the machine. It's the stainless steel high vacuum system. But and on the other part, when you are with MOCVD, it's not, okay, it's not comparable. But again, I repeat, as you do a lot of different alloys, sophisticated material, so you need to have experience and knowledge on that.
So you're not willing to make a recommendation, say, with very few arguments going one way or the other way. You also, in fact, think that MBE has a role to play. MBE, of course, means molecular beam epitaxy, where materials are normally evaporated from the solid state through the liquid phase and into the gas phase. You don't want to qualify, say, that everybody should go for MOCVD and they should leave MBE aside. That's not what you're saying.
I never recommend the people to do MOCVD or MBE or liquid phase epitaxy, anything, because each of these techniques has their own applications. For future, something that unfortunately in a short discussion like that, in this interview, it's impossible to explain the advantages of each of them and the utility of each of them. But the future system is something that to combine the advantages of all of them. It depends what's the application, it depends what's the use of that. But something that it's for future, it's a kind of combination of both technique, MBE and MOCVD, and giving the advantages of liquid phase epitaxy and vapor phase epitaxy. The technique that we need in future is something that to put the substrate on one part and to have the integrated circuits and the device on the other part. And it's not possible to do that only by MBE or only by MOCVD. Is development of a new technique that is the combination of both of them. I started here and I'm going to continue for to do that, and there are a lot of work for that for the future.
Thank you very much.
Parfait.
On coupe ici parce que maintenant...
Tu déclenches? On attend 20 secondes. Donc la première question, vous avez été très long.
Oui, mais et j'oublie maintenant tout ce que je dis sur Européis, parce que je n'ai pas voulu rien dire sur Européis, ça je laisse tomber maintenant. Maintenant, on parle de Madame Razeghi et pas d'Européis. Non, mais c'est seulement pour me chauffer un peu aussi.
Parce que votre question faisait 1 minute.
Oui, non, mais maintenant ça veut faire 10 secondes, je vous promets.
Un peu plus que 10 secondes.
Oui, un peu plus.
Non, moi je dirais qu'il faut que ça...
Oui, c'est un peu... Mais là, il faut écrire avant. Si on fait des questions comme ça, 10 secondes, il faut avoir tout écrit en avant. Et c'est très important, normalement. Mais je n'ai rien écrit parce qu'on n'est pas sûr. Ok, on est prêt, on tourne? Ok. Madame Razeghi, we're very happy to have been able to capture you between a meeting in Italy and between a meeting in the US next week. We would like to take this opportunity to get closer to you, to let the people who are watching our programs get a feeling for what kind of person you are and what you've been doing to science and technology. In the opening session of the conference in Aachen that you were presiding and chairing, you were, among a lot of other good suggestions, saying, don't forget that the whole thing is basic science. It depends on basic science in materials, and technology is getting nowhere if basic science is being left out. You are a scientist in Thomson. Are you able to do basic science?
Parfait.
C'était là la question.
Très bien.
Exactement.
Ça, c'est très bien.
2 heures.
Question 1, c'est 203. Maintenant, vous me refaites la question. In MOCVD, what is the material essential?
What is the essential
Material.
element?
Material essential. Ce que vous voulez.
Quand vous avez commenté les sécurités, j'ai voulu discuter le réacteur, mais ça va quand même.
Elle a repris d'ailleurs, je crois qu'elle a parlé de matériaux, non pas d'éléments. Quand vous voulez.
Oui. On prend le livre.
Alors attendez, montrez-moi quand vous voulez faire là. Oui, d'accord. On ne voit pas beaucoup à l'écran. Alors si vous voulez faire ça, les garçons, vous faites un plan plus large. Vous allez rester un peu.
Oui.
Très bien. Voilà, c'est bon là, quand vous voulez.
What is the key element of MOCVD?
Vous me donnez le numéro de compteur et on va la refaire. Parce que moi j'avais in MOCVD. Je sais pas.
In MOCVD.
303, 313.
Quand vous voulez.
La même chose. What is the key element in MOCVD?
Refaites-le dans... Parce que là, les questions les autres que vous avez posées, vous les avez posées plus. Réessayez in MOC, unknown, pour faire un lien avec ce qui s'est passé avant. Unknown, in MOCVD.
Okay. And now, let me ask, what is the central element of MOCVD?
D'accord, parfait. Maintenant, ce que je voudrais, c'est que on fasse... On le lit.
Donc je vous regarde. Faut sourire.
Vous ne parlez pas, parfois? C'est bon. C'est combien là? Ça tourne?
Mais il faut 15 secondes de fatigue.
C'est combien là?
4,50, on est parti à peu près.
Hocher un peu de la tête. commencer. Hein. Voilà. Tu as laissé enregistrer?
Ça part. On a ça, il n'y a que 5 secondes.
Tu me dis combien c'est?
5-20.
La caméra bouge là. Dites quand vous êtes prêts. Philippe, tu fais bouger la caméra là. Hein. Ne reste pas près d'elle.
Je peux commencer. Eh bien, on va seulement un tout petit peu commenter ça. C'est combien de temps j'ai à peu près?
Si on peut faire en 5 minutes, ça...
C'est beaucoup ça, c'est énorme.
Oui, je sais. Vous voulez utiliser seulement un des dispositifs là et
Oui, parce que ça, justement, ça c'est un peu...
l'histoire, mais vraiment des points.
Exact.
Il y a un truc que il arrive un peu plus vite pour qu'on voit le Thomson CSF complet, parce que là on a le coupé de thé, c'est pas juste. Voilà, merci. Parfait. Très bien, très bien.
One of the dream for future is concerning material, device, and physics. And for application of system application is to combination of different kind of material of 3,5 and silico substrate. Here you have an example that, of course, it's the first, again I repeat, is the first realization in the world. But we hope that thanks to the technique of emissivity and also MOMB for near future, we are going to be able to use, as you can see here we have a 6-inch diameter silicon substrate. That's the substrate that you can see here. To put on that the gallium arsenide 3,5 base material to do very high speed transistor on that. And at the same time, to put another kind of material. It means that indium phosphide and quaternary systems for optical device. To put them together and to have the monolithic integration of optoelectronic device for system applications, not only on the Earth, but on the space. And we are not going to the detail, but that's the dream. Why? Because you have the advantages, all of this material, to put them together and to have very sophisticated systems that can in future play as our eyes or as our brain. So that's the dream for future. And I have to say that it's thanks to this technique, and we did some demonstration, because in the world, everywhere, without to have the demonstration, nobody can believe. Somebody has to do something, and after that, to show a demonstrator, to show the feasibility, and the other laboratories in the world trying to follow them. So we were again pioneering, we did again pioneering work in this field in the world. Of course, when you are in Japan now today, when you are in United States, they say that, okay, it's only at Thomson that they did the first laser on silicon, or we did. But you have to know one thing. These wafers that I showed here is coming from United States. It's coming from Kopin Corporation, that they are the people from MIT. But the president of MIT, that they did it, and he gave a very nice talk at SPIE conference. He came here and he told that if I put a 1.3 micron lasers on silicon substrate, they are going to give me as a gift. So that's the unique wafer in the world. And he came here and to bring it to give me as a gift. And again, I have to tell you, it's only unique in the world. But the laser that we did gave a lot of importance to his work. So that's again another result which comes from research at Thomson, thanks to technique of emissivity.
Ce que l'on va refaire maintenant,